I will now go over a general solution for a second-order linear differential equation as it applies to transient circuits, to second-order transient circuits. So a linear differential equation of the second order has this particular form, and what we see is a x of t applies to, it could be a current I or voltage V. So generally speaking, it doesn't matter. Both of them will have the same form. And what you see is the second derivative of some sort of a function, and then the first derivative of a function, and then the function itself equals what we call a forcing function. And I've written it in such a way that the coefficient for the second order derivative is just 1, and the rest of them will be a1 and a2. And math tells us that a solution for this has two forms. X of t will have a solution that is particular, we call it the particular solution, and another one which is complementary, so it's a complementary solution. Let me just write it here. So this is a particular, okay, solution, and this one here is complementary solution. This is a complementary solution. All right, so the particular solution, as it turns out, it applies and it's based on the shape of the forcing function. I'll show you a solution and how we solve it. However, the complementary solution, the way we get the complementary solution is simply by saying, well, we'll have this differential equation, which is based on the original. It's pretty much almost the same as the original second order differential equation. The only difference is the following in here, actually. So instead of having a forcing function, what it will have, it has a 0. So no forcing function. And before I continue in showing you how to find the particular solution and the complementary solution, I want to do a simple change of variable. So what I'll do is I'll tell you, you know what, let's consider that A1 is just simply 2 alpha, and A2 I'm just going to consider it to be omega 0 squared. So the reason for this change will become apparent when we talk about the complementary solution. It just simplifies terms later on. So if I'm rewriting this differential equation, it would look pretty much almost the same, except that I will have 2 alpha in here, and that's dx of t divided by d of t plus omega 0 square x of t, and that here is still a forcing function. Okay. All right, so let's now focus on that particular solution. So the particular solution xp of t happens to be based on the shape of the forcing function. And in this table, what I'm showing you is different forcing function shapes. And as it turns out to be, if the forcing function happened to be a constant, the output will be constant. If it was of the shape of e, basically it's exponential, so the output will be exponential, but with different forms depending on whether something happened to do with the characteristic equation, which I'll cover. If it's sinusoidal, it's also a combination of sine and cosine, and the same if it's a combination of sine cosine, it's also a combination of sine and cosine. If it's polynomial, it's also polynomial, and so forth. In this part of the course, what we care about is this particular solution, and the reason why is because we're dealing with DC sources that are constant, so the forcing functions will happen to be constant, so the solution will be constant. And if that's the case, what we can say is, well, the solution for a second order differential equation that has a forcing function a that is constant is simply constant. So we know that the particular solution is constant. Well, the derivative of a constant is 0. The second derivative of a constant is 0, and the first derivative of a constant is 0. That leaves me with omega 0 squared. That's here is the particular solution equals a. That means the particular solution, we can get it by simply dividing that number a divided by omega 0 squared. And that is the particular solution for a constant forcing function. All right, so that's the particular solution. Let's move on to the complementary solution. So as a quick reminder, the complementary solution applies to the same differential equation, except now we don't have a forcing function. We just put a 0 in here, and that's a homogeneous equation. Okay, so what we have is the following. So math tells us what we're interested in is a function added to its derivative, added to its second derivative, and for something to work, they have to have some sort of a same format or shape. And as it turns out to be, the exponent is actually a good function, a good candidate, and a valid candidate for a solution. So we can say that a valid solution for a complementary solution here is of the shape k e to the power s of t. And of course, we can do the following. Well, if it's xc of t is this one here, for example, we can figure out the first derivative and then the second derivative and just substitute them. So we can say the first derivative of xc of t is just simply k s e to the power s of t, and the second derivative that will be, this is here c, dt squared. That's basically k s squared e s of t. So I'll take all these three, basically this, those, and that, and just substitute in here. So the second derivative in here, what I have is k s squared e s of t plus 2 alpha, and that's the first derivative, that's k s e s of t, and then no derivative, and that becomes, I believe there's a factor omega 0 squared, or coefficient k e s of t equals 0. What I'll do is I'll factor out k e s of t, and that will leave me with s squared plus 2 alpha s plus omega 0 squared equals 0. Okay, and as it turns out to be now, if this is equal to 0, that means a few things that might be equal to 0. So you can, for example, tell me, well, k is equal to 0. But if k is equal to 0, that means the solution I'm assuming in here is 0. That means I'm telling 0, 0, 0. Well, while it's a valid solution, it's not an interesting one. And it doesn't actually apply if we have currents, basically initial currents flowing through an inductor or initial voltage flowing across a capacitor. So k is not going to be equal to 0. I'm not going to be interested in such a solution. The other thing that cannot be 0 is e to the power of s of t, because well, t has to go to infinity basically, or to negative infinity, for that to become a valid solution. So that is not, well, actually it cannot be 0. E to the power, unless it's negative infinity, cannot be 0. So that leaves us with the following equation, which is s squared plus 2 alpha s plus omega 0 squared equals 0. And this here is what we call a characteristic equation, or sometimes we refer to it as the auxiliary equation. So the roots of this characteristic equation or auxiliary equation can be computed using the discriminant. So delta is just simply b squared, which is 2 alpha squared minus 4 times 1, which is a times omega 0 squared in here, which you can just basically say minus omega 0 squared in here. And well, that tells me that it's 4 alpha squared minus 4 omega squared. Okay, and that's basically the delta. So the two solutions, the two roots of this quadratic equation is simply s is just negative b, which is 2 alpha, plus the square root of this here, 4 alpha squared minus omega squared. I just basically rewrote this here, okay, divided by 2, okay, which is 2 times a, and the a's 1 happened here. Okay, and that tells me that this is simply negative alpha plus the square root of alpha squared minus omega squared. And hence the reason why I basically rechanged the a1 and a2 to alpha and alpha 2, because I knew that this will happen here. So that tells me that s of 1 is just simply negative alpha plus the square root of alpha squared minus omega squared. Similarly, you can tell me, well, s of 2 is just simply negative 2 alpha. Now it's negative 4 alpha squared minus omega squared, okay, divided by 2. That means that the second root is negative alpha squared minus omega squared in here. All right, so a few definitions of these terms. So what do they mean? As it turns out, that alpha is what we call the Neper frequency, okay? Frequency. Sometimes we call it the damping frequency or damping coefficient, and its units is usually radians per second. Sometimes I've seen them as Nepers per second. Okay, omega 0 is also a frequency, and this is usually called a resonant frequency. Okay, and its units is also radians per second. Sometimes we also call it the undamped natural frequency. And I've seen certain places, well, they tell me, you know what, zeta is just simply alpha divided by omega 0, and this is a unitless, and this is typically called a damping ratio. Sometimes people use that damping ratio. So instead of alpha and omega 0, some people just use the zeta. Okay, for now I'll just focus on alpha and omega 0. This is how my solution will just contain alpha and omega 0. It will not contain these, but if you see it, it's just simply just a change of variable. Of course, we assumed that the solution of that differential equation happened to be, if you remember from here, what we did is we said, well, the complementary solution is simply ke to the power s of t. Well, I have two s's. That means I have the first complementary solution, and that's basically k1e s1 of t, and also kc of t is also a solution, which is k2e s of t. All right, and in math, they told us, well, both of them are valid solution, and also what we can do is we can say, well, the real solution or the actual solution, or not the real solution, another valid solution is just simply the sum of both these solutions is also valid, es1 of t plus k2 es2 of t. And if you doubt it, what you can do is you can take this here, I'll highlight it, okay? What you can do is you can take it, you can just substitute this particular value in the original differential equation in here. Basically, take the first derivative substituted in here, take the second derivative substituted in here, you should end up with a 0, just to prove that this is actually a valid solution. But anyway, I will not do this here for the sake of time, okay? What I can tell you is the following. So the complementary solution is of this form. So in summary, the complementary solution is the solution of what we call a homogeneous equation. It's the original differential equations, and instead of having a forcing function, we put a 0 in here. So we ended up with a characteristic equation. You can go through the derivation, but it's really straightforward. If you have the original differential equations and the coefficient for the second derivative is just 1, you can simply just derive the characteristic equation directly. So you will have s squared, and this one here, this whatever you have in here, that will be the 2 alpha, and whatever you have in here, it will be the omega 0 squared, and that's the characteristic equation. And of course, it's a quadratic equation, so based on the value of alpha or delta, well, alpha and omega is 0, so if you compute the discriminant, it's a quadratic equation, so we have two solutions. This is S1 and S2. So alpha, we call it the Neper frequency, omega 0, we called it the resonant frequency, and the ratio between them is the damping ratio. So the complete solution for that differential equation of this particular is this particular shape. So it has the particular solution depending on the shape of the forcing function and the complementary solution. So that's how that solution for the x of t is. And x could be voltage or current. Now, there's a couple of things that we need to pay attention to, and these are K1 and K2. And as it turns out to be that these are just constants, and these constants can typically be computed using two equations. And these two equations typically rely on initial conditions of the circuit, like what voltages and currents are flowing through that circuit initially. So one easy way that we can compute these K1 and K2 is by simply, you know what, let's take a look at t equals 0, which is the initial condition. So what you can say, well, x of 0, and again, x of 0 could be the current, the voltage across an inductor, capacitor, whatever it is. And then you can tell me it's xp evaluated 0 plus k1 e to the power, well, e to the power 0, which is just simply 1, plus k of 2, which is also e to the power 0, which is 1. Okay, that means what you can tell me is simply k1 plus k2 is simply x of 0 minus xp of 0. Okay. And the x of p again, for DC sources, this is just constant for DC sources, for DC. All right. So this is one equation that we'll be able to use to compute K1 and K2. So what's another equation? Well, the second equation that we can use is the following. We can just take the derivative of this equation in here, and we can evaluate it at t equals 0 at the initial condition. And if we take the derivative of this one here, it will be the following. So I'm going to take the derivative of the complementary solution first, and that's simply K1 es1t. Of course, what we have to do is, since we took the derivative, we have to multiply by s1 in here. Similarly, K2 s of t es of 2 of t. Okay, plus, well, typically we say, well, the derivative of xp of t divided by d of t, and this, all of them are evaluated at t equals 0. So let's substitute. So the first derivative of the current, voltage, whatever it is, evaluated at t equals 0 will be simply k1 s1 because e to the power 0 is 0 plus k2 s2 because e to the power 0 will be 0. And typically here for DC, I'm just going to say this is 0 because remember xp of t, the derivative of a constant will be just simply 0 for DC. Okay. So this is the second equation. So what we can do is we can say, here's the first equation to compute K1 and K2, and here's the second equation to get K1 and K2. And so the initial condition, you just basically substitute t equals 0, and you substitute it, you'll get K1 plus K2, and then you take the derivative of that x of t, including the particular solution here. You take the first derivative evaluated at 0, you'll get the second equation. So you solve these two equations, and you'll end up with a solution that contains the value of these constants. So I have previously mentioned that the solution is of three cases: overdamped, underdamped, and critically damped. So where does all of this fit within this solution? So as it turns out, the complementary solution here contains what we call the characteristic equation, and I mentioned that it contains, well, it's a quadratic equation, so it has one root and a second root. Well, as it turns out to be, that these roots have different versions. So if these roots happen to be, for example, if alpha is greater than omega 0, so that means the discriminant, and it's like everything in here, the discriminant for this one here, those two solutions in here will be S1 and S2 will be all real. So alpha is a positive term, so this is negative, and this is a positive term, this is negative, so negative minus negative. So what we'll end up with is a couple of real and distinct solution, and that will be the overdamped response. However, if it happened to be that alpha is smaller than omega 0, well, that means this term in here under the square root will be negative. That means we will have some complex numbers in here. So as it turns out to be, this, if the S1 and S2, which are, this has to be S2 in here. Okay, so if S1 and S2 happen to be simply the two complex conjugate, what we end up with is an underdamped response. And if alpha happen to be exactly equal to 0, that means the S1 and S2 are exactly the same, and they're both negative alpha, which are not distinct, they're double, and they're real. And in that particular case, the solution will be what we call a critically damped. So we only have one, and as it turns out to be, that the solution we have is not the case. So I'll cover each one of these cases in details in the following videos.